Well, good afternoon, everyone. I am Vince Sprinkle. I'm the Senior Strategic Advisor for Energy Storage at PNNL. And it is my pleasure to welcome you to our Energy Storage at PNNL webinar series. So this is the second in a series we have planned out through the summer and will continue into the fall. And the goal of this series is really to start looking at to explore the research that's going on at PNNL that's impacting the ultimate deployment of energy storage technologies and how that research is going to impact the newly announced grid storage launchpad that's being built at PNNL and slated to open in 2023. That grid storage launchpad that you saw a picture of up earlier is really focused on how do we accelerate that next generation of storage technologies. And to accelerate that, we have to have a holistic view of particularly how these systems are going to be used when they are deployed in the field. And so with that, we're happy to have Dee Wu with us today from PNNL to talk about energy storage analytics and how you look at these systems when they are deployed out there. That deployment data, that usage, the optimization of those storage systems when they're employed in services is the information that we need to feed back into GSL and have along the entire way of the research and the development program. So a new technology that is starting today would be developed to where towards a specific use case and tested under there. And so as you build it up from a new anode into a full cell, into a prototype, into 100 kilowatt, you have that consistency and application-driven development. And through that, we're hoping to accelerate it. And so hopefully we'll as you go through and hear Dee's work, what we're doing, you can see that thread and how it will tie into the grid storage launchpad. So Dee's got a presentation here. I'll do a quick intro. But then we'll have about 15 minutes at the end for your Q&A, and we encourage you to post your questions in the chat, and we'll be aggregating those and then doing a Q&A at the end. So with that, let me turn to introducing our speaker, Dee Wu, and let Dee get started. So Dee Wu is our Chief Research Engineer and a team leader within the Optimization and Control Group at PNNL. He received his BS and MS degrees in electrical engineering from Shanghai Jiao Tong University in China, and a PhD in electrical and computer engineering from Iowa State University in 2012. At PNNL, Dee leads the research work in the areas of grid storage analytics, buildings to grid integration, microgrid design, and hybrid energy systems. Dee is a senior member of the IEEE and a member of the IEEE Power and Energy Society and Control System Society. He serves as editor of IEEE Open Access Journal of Power and Energy and is a former secretary of Working Group on Economics for Energy Storage and co-chair of a working group on microgrid business and use case development in the IEEE Power and Engineering Society. So with that, Dee, thank you very much for your presentation today, and I'll turn it over to you. Thank you.
Give me a second. Let me figure out how to share my screen here. Okay. Can you see my screen okay?
Yes, we can see it fine, Dee.
Okay, great. All right. Thanks, Vince, for the introduction. Thank you, everyone, for joining us here today. The second presentation of the webinar series. My colleague, Matt Pace, talked about energy storage safety 2 weeks ago. And in today's presentation, I'll talk about energy storage analytics. Okay, so here is the outline of my presentation. So first, I will briefly describe various services that can be provided by energy storage and the need of advanced energy storage analytics. Next, I will talk about the storage evaluation tools we developed and provide an overview of storage assessment project at PNNL. I'll also briefly describe modeling, control, valuation, and sizing method we developed, which are essential for the tool development and project assessment. And finally, conclusions and future work will be offered. Okay, so energy storage can help solve problems in all parts of the grid and hold a great potential in meeting resource and transmission adequacy. Broadly speaking, there are 3 types of resource adequacy, including system capacity, flexibility, and local capacity, each designed to keep the grid operating under different conditions. Transmission adequacy is needed to support balancing load and generation and support competitive markets. There are couplings between the two. For example, additional transmission capacity enhances the capacity value of variable generation. Energy storage and other resources are non-value alternatives, elevating the need for T&D investment. So at the lab, we have studied various energy storage systems, such as battery energy storage, hydrogen energy storage, or power-to-gas system, small modular pump storage hydro, plug-in electric vehicles and buildings as storage assets. So this storage can provide a broad range of applications, as listed on the right, based on how power system is structured, including bulk energy, ancillary, T&D, and customer services. Due to time limitation, I won't go through each of these services. Please refer to the paper at the bottom for additional information. I'll also talk about some of these services later when I present examples of assessment projects. So during the past few years, the development of energy storage has been gathering momentum. Technology has advanced, technical feasibility has been demonstrated. There are all kinds of demonstration pilot projects for different use cases and applications. Nevertheless, not many of them are truly cost-effective. Value streams need to be identified and properly monetized, and capturing stacked value stream in system design and control development is important for a project to be economically viable. The lack of the ability to value energy storage systems became a significant barrier to their penetration in the marketplace. So to address the challenge, several energy storage evaluation tools has been developed. For example, at PNNL, we have developed a suite of tools named eSet to enable various stakeholders to model, optimize, evaluate energy storage and hybrid systems, considering a broad range of grid and end user services and applications. Currently, eSet consists of 5 modules dedicated to different energy storage technologies and storage-enabled microgrid. And last year, we made a subset of features and capabilities of eSet publicly accessible as a web-based tool that can be used across different platforms and devices. Here is the link to the web-based eSet. And in eSet, we have developed energy storage models with different level of complexity and fidelity to represent different energy storage and hybrid systems. Modeling of various services is consistent across 2 different eSet tools and different energy storage technologies. Advanced optimization and control methods are used to define technically achievable resiliency benefits as well as environmental and economic benefits. We have also integrated various databases of utility rates, electricity market prices, renewables, and building loads. We are currently working to integrate the energy storage cost database. eSet has been licensed and used by more than 300 users from more than 200 institutions. About 83% are external users. And here is the count of users by institution category. So currently there are about 150 industry users, including around 20 utility users. Many other utilities prefer to directly work with us and perform comprehensive analysis instead of running the tool themselves. And there are about 70 users from national labs and 55 from universities and 15 from federal and local governments, including DOE. So in addition to eSet, there are also several other DOE evaluation tools. including DIRCAM, developed by Lawrence Berkeley National Lab, Quest, developed by Sandia, Reopt, developed by Unreal, and so on. So it's not easy for general users to understand how these tools are different in terms of functionalities and capabilities, and therefore select the most appropriate tools to meet their specific needs. So therefore, as an effort of DOE Energy Storage Grant Challenge, or ESGC, a web-based model selection platform has been developed. The core of the platform is based on the specification discovery procedure and the engine that dynamically calculates scores for different tools, and the users are guided through the model selection process. By collecting the answers to a set of questions regarding the valuation analysis to be performed, the desired capability and needs are discovered, and the tools are scored and recommended. So in the first version of our tool launched earlier this year, 5 DOE evaluation tools are included in the MSP. And there are also an ongoing collaborative efforts among 3 ESGC tracks to integrate 70+ DOE models and tools into the MSP. The techno-economic assessment can be very complicated. Different configurations and sizing options must be considered. The corresponding physical capability and potential value streams need to be properly modeled. Valuation also involves optimization, control, simulation, in addition to economic analysis. There are different deployment scenarios. For example, energy storage can be invested and deployed in a vertically integrated utility or by a third party participating in electricity markets, which will affect the value propositions and potential applications. So even for the same use case, same application, the values vary much by region and system, depending on numerous factors such as generation mix, grid infrastructure, market structures, and rules. So at PNNL, we have accessed energy storage and microgrid system at more than 30 sites across the US as highlighted on this map. Most of these projects are battery or battery-enabled microgrids, and there are also several non-battery systems, including some hydrogen energy storage system, buildings as storage assets, and the pump storage hydro. So in this project, we work with utilities and other stakeholders to identify different deployment options, use cases, and value proposition. We develop system and component level models, optimization formulation and control algorithms required for planning and operation. We also work with utilities to develop data requirement, collect the data or generate the required inputs, and then perform comprehensive assessments, include all kinds of sensitivity analysis. And some projects were completed within a year, while others last multiple years, including economic assessment at the planning stage, testing and collecting measurements after deployment, and also assisting advanced control implementation. So I'll provide a few examples of these assessment projects next. Okay, so in the first project, collaborating with Portland General Electric, we have evaluated a 5 megawatt, 1.25 megawatt battery at Salem Smart Power Center in Oregon. The center was developed in the Smart Grid Demonstration Project launched in 2010 and co-funded by DOE, focusing on R&D demonstration. Cost effectiveness was not the emphasis. So therefore, the system was underutilized, operating on an average of 14 hours per month, mainly for primary frequency response. Then in 2017, we worked with PGE to explore additional value streams, including energy upcharge, demand response, regulation up, regulation down, spin and spin reserve, and water services. So we first evaluated benefits from each of these services individually. And here is the sum of the benefits without considering the trade-offs or double counting, which is technically unachievable. So then we run the optimization considering the computation trade-off among them, and we obtain the maximized benefits from the stacked value stream. So we found compared with primary frequency response only, we can generate additional $170,000 annually from the stacked value stream. And in another project, collaborating with National Grid, we evaluated a 6 megawatt 8-hour battery at Nantucket Island in Massachusetts. The power was provided to the island through 2 submarine cables, as shown here. To ride through N-1 contingency, a 3rd submarine cable would be required. An alternative solution was to invest in a battery plus combustion turbine generator. The benefits from deferring the investment of the 3rd cable is big enough for the project to be cost effective. We have also worked with National Grid to evaluate the benefits from other services as listed here. With the stacked value stream considered, the benefits to cost ratio is about 155. And benefits are largely driven by the transmission deferral use case, accounting for about 75% of the total benefits. In a recent project working with electricity, we have evaluated a 5 to 10 megawatt and 1 to 4 hour lithium-ion battery for capacity charge reduction. So currently, electricity's member utility purchase power from Duke Energy Progress under a long-term purchase agreement. So they need to pay the capacity charge based on their coincident demand during Duke Energy Progress system peak hours. So with a rate of more than $20 per kilowatt per month, investing in energy storage for capacity charge reduction is a pretty easy business case to make. So the technical challenge is that electricities and their member utilities don't know exactly when the peak hour will occur. Discharging battery during all high load hours will speed up the degradation, and there is also a risk of missing system peak hours. So therefore, advanced control, valuation, and sizing methods are required to better address the operational uncertainties considering battery degradation effects. So we have developed a 2-step dispatch and evaluation framework that seamlessly integrates the load forecasting and the charging control. So we have worked with electricity to obtain and back forecast the DEP system load for 21 years, and using 15 of them for model training, and using 6 of them for testing. And here are some testing results. For example, for the 2-hour battery energy storage, we are able to capture peak hours in 10 to 12 months a year, with the battery only cycled 7 to 8 times per month. And here is the cost versus benefits and also the net benefits. As can be seen, the 2-hour battery energy storage results in the maximum net benefits. On the other hand, 4-hour battery energy storage can help mitigate the risk of missing the system peak load. And also the increased duration help to mitigate the battery degradation by reducing the depth of discharge. So in our ongoing project, Sandia and the PNNL are working with NRECA and 4 co-ops to use battery energy storage system to improve rural resiliency. PNNL provide technical assistance to the last 2 projects in this table. Both are facility microgrid at the military base. And with the existing diesel, microgrid cannot survive extended outage due to limited on-site fuel storage capacity. The idea is to use battery energy storage to recover the fuel that would be otherwise wasted in a load bank when the building load is lower than the minimum loading level of the diesel gen set, and use battery flexibility to improve the fuel efficiency. The battery can also be used to provide other services such as water wire support, the power factor correction, demand charge reduction. So here are the resiliency assessment results for a 2-hour battery energy storage at Ellsworth Air Force military base. So this plot shows the cumulative distribution function of the fuel consumption for outages with different durations and in different seasons. And this vertical line shows the on-site fuel storage capacity. So without the battery, the system cannot survive any outage longer than 2 days. And with battery energy storage, because of the improved fuel efficiency, there is enough fuel for most of outages up to 5 days in winter months. And in summer, the survivability is lower due to the higher load, but the microgrid is still able to survive all 3-day outages and with a survival rate of 60% for 4 days outages. Okay, so this is the last example of the assessment project, which is also an ongoing project working with Vista and the Washington State University. We evaluate a shared energy economy model palette, considering various DERs, including 2 buildings with advanced building management system, 2 100 kilowatt photovoltaic, and 2 battery energy storage with a total capacity of 1.8 megawatt hour. And these DERs can be shared and used for multiple purposes and provide various end user and grid services. The goal is to demonstrate how both the customer and the utility can benefit this shared energy economy model. And here is the initial resiliency analysis results, considering different outage durations. And we found that there is a good chance to survive an outage with a 2-hour duration. Load shedding and additional DER is required to further enhance resiliency. Here is the economic and benefits cost analysis. So the benefits from behind meter application grid services are aggregated and showed as a negative cost. So as can be seen, the benefits and the costs are almost breaking even, and the net cost is close to 0 for the improved resiliency. So this means that the shared energy economy model could be a more cost-effective solution compared with conventional digital genset for improved resiliency. Okay, so next, I'll briefly describe some modeling optimal control dispatch and valuation setting method we developed and also used for tool development and project assessment. I will stay at high level, but provide references that contain detailed information, results, and some methods. Let's look at the modeling first. So energy storage model is a set of equations and constraints or tables representing operational flexibility and physical constraints. Often it's a black box or gray box model at the system level. So relaxed and approximate model are commonly used. So it's very important to maintain a good balance between fidelity and simplicity during the evaluation analysis. Technical characteristics vary much by technology. So do the models used in evaluation. So as an example, some key attributes considered in modeling battery PSH and also hydrogen energy storage are summarized here. And I will provide additional information in the next few slides. Okay, so for battery energy storage, we need to model operational flexibility and degradation effects. Constant efficiency model with static operating range is the easiest one, and also is the most popular method to model operational flexibility. However, such a model may not be able to fully capture operational characteristics of battery energy storage, especially for flow batteries. For example, here is the change of state of charge with different charging discharging power levels for 1 megawatt, 3.2 megawatt hour unit energy vanadium flow battery system. As can be seen, the charging discharging power capabilities varies with state of charge, and the change of state of charge rates also depends on both power and the state of charge levels. To better model the physical capability of a battery energy storage system, we have developed a generic high fidelity model, which can be constructed using testing data, as listed here. Machine learning methods such as gradient boosting machine algorithm can be used for ranking predictor importance and also determine the corresponding coefficient. So for hydrogen, modeling methods are required to represent system operation toward multiple energy delivery pathways and grid services. And this picture illustrates the scope of the hydrogen energy storage system we considered. The electricity from the grid can be used to produce hydrogen through electrolyzer. And the produced hydrogen can be used as clean transportation fuel or injected into gas network, either directly or after methanation, or mixed with some existing gas. And also the hydrogen can be used to produce electricity to support the local load or feed back to the grid. Simultaneously, because the operation of electrolyzer and fuel cell are flexible, can provide various behind-the-meter and grid services. So for valuation of such kind of system, so we need to model economic and technical characteristics of individual components, such as electrolyzer, fuel cell, compressor, hydrogen storage, either long duration or buffer storage, or potential methanation reactor. We also need to model individual pathways and also their couplings, various grid services, and also the trade-off of different benefits. So all kind of modeling is required. And my colleague Jamie Holliday will talk about hydrogen energy storage in a future webinar, also in this series in July. So when modeling pump storage hydro, different technology and configuration must be considered. So for example, with the fixed speed technology, a unit cannot be operated at the varying pumping power. And with adjustable speed, a non-synchronous pumping speed can be achieved, increasing the range of pumping power. And we also need to consider different configurations. And with reversible pumps and turbines, pumping and generating cannot occur simultaneously at the unit level. And with ternary units, we can couple or uncouple the pump from the shaft, and therefore provide a flexible operating range through hydraulic short circuit. So in addition, the hydraulic short circuit at plant level also help increase the flexibility of the system operation. So this picture illustrates the operation power range versus flow rate in different mode for a ternary set unit level at unit level. And this picture on the right illustrated the unit and plant level operating range for fixed speed reversible pump and turbines. So as can be seen, although the fixed pumping power can only be realized at the unit level shown here, but for the entire system, because of the plant level hydraulic short circuit, we have the increased operating range in the pumping mode as shown here. Okay, buildings. So building can be used as a storage asset, and thermal storage capability in building mass and a flexible thermostatically controlled load represent largely untapped resource for flexibility required by the grid. The challenge is how to model flexibility and coordinate building assets with other resources or a large area at the system level. Battery equivalent model from aggregated buildings is a promising technology. So here is a picture illustrated the idea, which shows a scalar linear system that resembles a simplified battery dynamics, parameterized by charging, discharging power limits, energy limits, and self-discharge rate. So many factors affect battery equivalent model parameter estimation and value, including resource type, the number of resources, system parameters such as the COP, the thermal resistance, capacitance, and also the external drivers such as ambient temperature, water draw, and so on. So there are three types of method estimating parameters of the battery equivalent model, including analytical methods, optimization-based, and simulation-based method. And this picture illustrates an example of simulation-based method in which Energy Plus and Modelica are integrated. So there will be a future webinar dedicated to building as storage assets. As for PEV modeling, there are a few factors that differentiate them from stationary batteries, such as travel pattern, electric range, tractable energy from batteries, EVSE availability, and power rating. So we have developed PV mobility and charging availability models to quantify the flexibility, considering both driving power and also power exchange with the grid. As can be seen, we have a lot of conditional expression here, which makes the model complicated in charging control design and evaluation. Optimization techniques can be applied to generate equivalent simplified linear programming formulations. Okay, so storage value cannot be well defined without specifying charging and discharging control. Energy storage control is essential to maximize and harvest their potential benefits. And there exist control paradigms, including centralized, hierarchical, and distributed control. Co-optimal control for stacked value stream is now a standard practice for most of the energy storage projects. We have developed various dispatch and control methods and algorithms based on different techniques, as listed here. And I'm going to cover some of these control paradigms and the methods next. So distributed and hierarchical control are two alternatives to centralized control. In distributed control, an agent only maintains a set of variables and update them through information exchange with a few neighbors, as illustrated in this picture. And compared to centralized control, distributed control offers several advantages, such as avoid a single point of failure, increase the flexibility and scalability, better respect of privacy, and better utilize distributed computing resources. So one challenge is how to develop effective and efficient algorithms, considering potential network effects, such as time delay, packet drops. And during the past few years, various consensus-based algorithms have been developed. And another alternative is the hierarchical control, which could offer advantages in terms of computational cost and communication burdens over fully centralized or distributed control. And here is an example of hierarchical control for integrated coordination of DERs and demand response. And the model predictive control with linear programming is the most popular method used in energy storage charging discharging control. And there exists various formulations for different use cases with different energy storage models. So here is a representative example of battery energy storage charging control for bundling grid services. And in this MPC control, the control objective is to maximize revenue from stacked value stream over look ahead time horizon, subject to sets of constraints, including battery operation and rules requirements of different grid services. And this picture illustrates how battery is charged and discharged with different streams considered, value streams considered in control objectives, including battery only, battery plus balancing with T&D deferral and with water var support. So in addition to model-based method, there also exist various data-driven methods, especially deep learning-based algorithm for energy storage charging discharging control. And here is an example of learning-based control to assist the service restoration through storage-enabled microgrid. And for this particular application, data-driven method face practical challenges such as potential hazards to the microgrid during online training, and also very limited opportunity due to the low outage rates. So we have developed a deep reinforced learning from demonstration. The key vision is to initiate the algorithm with expert demonstration and enable the control agent to rapidly learn the safe enough policy for online implementation. And this occur during the pre-training stage. During online training stage, action clipping, reward clipping, and expert demonstration are leveraged to ensure safe exploration and accelerating the training process. And here are two examples of controls for buildings as storage assets. And the left one is a modified priority stack algorithm. This is for the residential thermostatically controlled load, which is essentially a rule-based method. And the right one is a hierarchical hybrid control, including both rule-based and optimal control method for adjusting zonal airflow in a commercial building. Okay, so valuation typically involves modeling and or simulating the integrated physical and control systems. We already talked about various modeling methods and also control design. As for the evaluation, the methods largely depend on use cases and applications. For a large utility scale energy storage system with a rated power more than 100 megawatt, a price taker model may not work. A more comprehensive system level analysis is required. And compared with evaluation for a given size of system, optimal sizing is generally more complicated, typically with additional assumptions made to simplify the problem. In many cases, deterministic methods are good enough, and there are also situations where it's important to model and handle uncertainties, and therefore require advanced stochastic method. The valuation may also involve nonlinear models in addition to the linear ones. Optimization techniques and tricks such as big M, piecewise linear, economic relaxation can be used to obtain the linear equivalent or relax the problem. And in addition to direct approach, iterative approach are also commonly used, such as iteratively simulating the MPC and real-time operations throughout a year to evaluate annual benefits, as illustrated here. That's for grid services. When the problem can be formulated as standard mathematical programming problem, off-the-shelf solver can be directly used. Otherwise, customized algorithms such as approximated dynamic programming, reinforced learning, particle swarm optimization, or hybrid approach need to be developed. So to describe the dispatch formulation and the evaluation procedure can also be applied to buildings as storage assets. And here is an assessment example of residential thermostatically controlled load in California, considering energy upcharge, frequency regulation up and down, spin reserve. It's found that using 20% of the residential thermostatically controlled load in California as storage asset can generate about the same level of benefits as a battery energy storage with 500 megawatt and 1 gigawatt hour capacity for these grid services. Building as storage assets have also been assessed for different distribution services, including distribution upgrade deferral, water loss support, and power factor correction. And this is an example of using residential air conditioner water heater in a feeder within Southern California Edison for power factor correction to meet the minimum limits. As for sizing, there are 3 types of approach, and we can formulate a large optimization with a rated power and energy capacity as the decision variable, and thereby capture the interaction between the system operation and system size. Analytical methods can also be used to determine the optimal size based on the objective quantitative analysis of cost and benefits. Here is an example of the analytical algorithm based on the demand charge reduction application. Bi-level optimization is a natural way for sizing. And at the bottom level, valuation is performed for a given size of energy storage. And at the upper level, searching algorithm can be used to find the optimal size based on the returned benefits from the lower level. Okay, so this is for the stochastic sizing. Okay, and two-stage stochastic programming is a framework for optimization that involves uncertainties and can be used for sizing. The first stage is to make here and now decisions, and before the realization of uncertain parameters is known. And in the second stage, given the decision from the first stage and after a random event occurs, we make a decision for the best outcome. To solve the problem numerically, probability distribution function of uncertain parameters and a finite number of scenarios are used to generate some deterministic equivalent. And based on this framework, we have developed a stochastic sizing methods for microgrid assets, considering both economic and resiliency benefits. And the first stage is the planning stage, as shown here, making the investment decision with uncertainties of system load, renewable generation, energy prices, outage starting time, and duration. Then the second stage is the operating stage. Given the DER sizes are determined from the first stage, operational dispatch is carried out in each scenarios in both grid connected and LND mode. Okay, so what have we learned so far? Okay, so first, system design and project development require appropriate energy storage model with a good balance between fidelity and complexity. And advanced modeling analytical methods are required to define the technically achievable benefits. And additional research work is required to select size and value storage with different durations for future decarbonized grid with high renewable penetration and with deep degree of electrification of transportation, building, and the industrial sector. And also improve the system resiliency against the extreme weather conditions. So many questions need to be answered and addressed. For example, how to advance the development and the deployment of energy storage and their market penetration through policy or market design, or come up with the incentive mechanisms, and how to coordinate a large number of energy storage at the system level. How much short, medium, and long duration energy storage we will need in future decarbonized grid, and how to model and address various uncertainties, like the uncertainty in technology development, long-term and operational uncertainties, random, non-random uncertainties. A lot of work to do. Okay, so that's all I have, and I appreciate the opportunity to talk about energy storage analytics, and thanks for your attention. I hope we have some questions that we can address.
Thank you, Dee. Yes, Laura put it in the chat, but please put your questions in the chat, and we will start the Q&A now going on. So Dee, one of the first questions that came up was, you had mentioned the usage of ESAT. Is ESAT open source, or what's the mechanism that people get access to ESAT? Can you explain that in a little more detail?
Sure, yeah. So currently we have two versions of ESAT. So one is the web-based ESAT, which is publicly accessible. And in my presentation slide, I provided the link to the web-based ESAT, and anyone can use it. And it's very easy and convenient. We already provide a template with the default parameters, and the user can download those parameters and template and modify the template and run the customized analysis. And currently, we haven't released the source code of ESAT yet, but that's something we plan to do. There is another version of ESAT, which is the in-house version of ESAT, which is more powerful. As I mentioned earlier, we plan to make the additional functionality we developed publicly accessible. It's still ongoing. So many utilities, they directly work with us to leverage and take advantage of the powerful in-house ESAT.
Okay, I'll ask another question here, and then I'll try to put a link to the ESAT page in the chat for people to see on that.
I can do that.
Or yeah, I'll let you answer the question, and then I can do it too. I was pulling it up there real quick. So one of the questions, or we got a couple that were similar. You know, you've taken this from basically starting off with a battery model, you know, and how to incorporate that, and have expanded it to hydrogen, you know, microgrids, pump storage, hydropower. Are there other technologies that may be more difficult? I mean, is compressed air energy storage viable to have in this system? Or any inroads to doing that? And then another question was on gravitational. Do you see any challenges getting that integrated into ESAT?
Yeah, that's a good question. So we haven't looked at those two technologies yet, but based on our previous experience on studying other technology, the proposed modeling framework, valuation framework, can still be applied. And we are currently working to integrate some kind of other evaluation technology, like, for example, hydrogen paired with hydro as a hybrid system, or battery paired with hydro to reduce the degradation of the turbine, geothermal paired with different battery energy storage. So as we go through this, a lot of lessons will be learned, and we will also look at other energy storage technologies.
Okay. And in all those cases, I mean, you need good economic data on what the CapEx of that system is and everything else that to feed into your model.
Exactly. Yeah, we need the capital cost, maintenance cost, and capture as we increase the usage of battery storage, how that will increase the operational cost. And there could be trade-off. We always need to identify the optimal control and maximize the total benefits, the net benefits.
Okay. We had another question that was talking about, how do you model for cost price fluctuations in there? How do you handle that uncertainty that's always in these systems? And you talk a little bit about the uncertainty equations that we need.
Sure. Yeah. So that's kind of one of the uncertainties I mentioned, long-term uncertainty, right? Like especially when you have energy storage with a lifetime over 50 years, sometime, for pump storage hydro, like 50 years. So there are a lot of uncertainty regarding the utility tariff or other energy system price, right? So for now, I think the most effective and easy method is the sensitivity analysis. And usually we run a lot of sensitivity analysis. For example, when we evaluate the back system, we consider different kind of water availability, like the drought year, average year, dry year, wet year, those kind of things. And also, usually you have a range of uncertainty. We are going to select enough number of scenarios to represent those uncertainties and capture the range of the net benefits. Usually, it's impossible to just come up with an accurate like one number, right? And sometimes utility prefer to generate net benefits in a range with expected net benefits.
So I would assume that same type of uncertainty, trying to build that into the initial models does go as you try to take this model with perfect foresight and turn it into a control algorithm. You need those same type of things to be able to make it an effective dispatch controller.
Yeah. So if you go to the web-based ESET, you will notice there is a checkbox ask you whether you want to use the built-in forecast model, okay? And without check that box, basically we are going to take whatever historical price or forecast price provided, and assuming we have a perfect foresight, and using that perfect foresight to schedule the energy storage operation and come up with the evaluation. And if you check that box, we will use the built-in forecast model to generate some forecast price, which is different from the actual price. Then that forecast price will be used for scheduling. And as we evaluate the benefits, we take the actual price. And we also show you the gap between using the forecast price and also the perfect price. And in that way, we help to address some uncertainties. And in many cases, we found without a perfect price, the benefits is only about 40 to 70% of the benefits with a perfect foresight.
Okay. All right, I think we've got a few more coming in here. I'll ask this one, and we may need to get a little more clarity in case you understand the acronyms. I don't. The question was, did you compare the performance between MPC and RL? Does that mean anything, or do we need other clarity?
Yeah. Okay, yeah, I know that. Yeah.
Okay. I'm glad you had it.
Yeah. Okay, so for MPC,
you might explain again for others though at MPC and RL.
Yeah. So MPC is the model predictive control, RL is the reinforced learning. Okay, and we tried both, and I would say it really depends on what kind of data and parameters are available. And let's say if you have a really good model, the model is very close to the actual system, MPC usually works best, right? And because it's also efficient, right? Because we have the very material solver to address the problem. And for RL, reinforced learning, it's really good weapon, excellent weapon to address uncertainties, and especially when we don't have a model, right? And through those kind of data-driven approach, just examine different actions and reward, by simulating the interaction between the agent and the environment, we gradually learn a good policy. And we found reinforced learning is very promising for energy storage to participate electricity market when there is uncertainties associated with electricity market price forecasting, right? And especially for long duration energy storage. And for short duration, like you have 2 hours, 4 hours, 8 hours, you only need to have a look at the horizon like within 24 hours, right? That's good enough. But if you have a long duration, you want to explore the opportunities for intraday or even interweek energy shifting. And there are lots of uncertainties, right? And for MPC, it doesn't work very well. But for reinforced learning, it works much better. And we are currently working on that. We got some progress. We are working on a paper to report the proposed method.
Okay, you mentioned long duration storage, and this is a topic that is quite prevalent at DOE headquarters right now and throughout the country. Both looking at those 12-hour solutions, weekly solutions, up to seasonal shifting of resources. In my experience, we don't have the same value proposition defined for long duration. Have you seen it? Have you been able to overcome some of those limitations looking at long duration? How do you handle that when it may not be as a mature market as we've seen with ancillary services, where we have a defined value?
Yeah. So that's also a good question. So for long duration battery energy storage, this is not well developed as short or medium duration. It's still in a nascent stage, both for the technology and the market mechanism, right? And so there is an increasing operational uncertainties, as I just described. And the benefits really depends on how we dispatch the long duration. And currently, I think we need advanced market design for both day ahead and real time. For example, for New York ISO, their real time market is only 2.5 hours. They only look at this short time window. And that window is not even enough for some medium short duration energy storage, like 4 hour, 6 hour energy storage, right? So therefore, decision support tool is required to improve their situational awareness for the operator in the system with a significant amount of energy storage or renewable penetration. I think it's likely that the market mechanism will be updated as we learn more, and there will be significant effects for the long duration energy storage market opportunity. And in addition, when you talk about value stream, right? So actually, many value stream applied to short duration, medium duration, also applied to long duration, but the magnitude of the value, the benefits are quite different, right? For example, when we evaluate the capacity benefits from energy storage, it's really based on the loss of load probability analysis. And for the short duration energy storage, because we also use energy storage for other services, therefore, whenever there is a peaker event, so we may not have enough energy left in the energy storage. Therefore, we need to apply a factor or credit when we calculate the capacity. But for long duration, that significantly increase the capacity credit. And also there is increased additional opportunity for intraday energy shifting, especially if you have, let's say, several hot days with electricity price higher than like $1,000 per megawatt hour, right? And for long duration, you can take advantage of the opportunity.
Okay, thank you. So one of the things that I think we realize, not only is this a valuable tool in terms of, looking at the optimal use and value proposition for deployed storage systems, but also from a policy perspective, as you mentioned, how do we get incentives? What would be the impact of incentives or other policy changes in there, and being able to model those, on a very locational specific system. Have you gotten much feedback from integrated resource planners at utilities in terms of trying to look at those kinds of activities and
yes,
policy modeling?
Yeah, so interestingly, yesterday, I just offered a presentation for the Duke Energy storage in RP workshop. And we talk about the challenge in modeling energy storage in their production cost modeling, and also how to capture the sub-hour benefits from energy storage. Because for their existing model, although they have the capability to model that, but their existing production cost model do not have the sub-hourly operation. So I think there are a lot of ongoing work, and we found that the system level analysis and also those kind of rate design are important for the energy storage deployment. For example, I just talked about the electricity energy storage assessment for capacity charge reduction, right? So that race was designed by Duke Energy Progress, right? And currently that race is high enough to make the energy storage investment cost effective. And what will happen in the future if we have significant amount of energy storage? And how about if Duke Energy, they are not able to recover the investment cost in the generation fleet, in the transmission distribution infrastructure, right? So I think they need appropriate design, not only for the developer of energy storage or from customer, but also for those utilities. And also previously, we worked with Hawaii Electric Company to evaluate the rate design of demand response program and encourage the distributed battery and photovoltaic. And we also learn a lot for different type of customers, what kind of demand response rate is appropriate to engage, to encourage their participation in the program.
Okay. Thank you. I know we're coming up on time. We'll try to get one more question here. I did want to point out that Laura has pasted the link to the ESET tool in the chat, that you can go check that out if you're interested. And I assume, Dee, that's got your contact information. If they want to get in touch with you and talk a few more. We're not going to have a chance to get to all the questions today. But, and one of the questions that came up is, is there a commercial opportunity for the tool? We're tasked as part of DOE to develop those tools that add to the public insight, that increase our understanding of how these systems are doing it. Do you see a commercial opportunity for that?
Yeah, I think at least many modules or some modules we developed can be integrated into many the existing commercial tools, because there are also some commercial tools dedicated to storage evaluation, right? But they're limited functionality or capabilities. And for example, the advanced load forecasting method can be integrated into the energy storage management system developed from different software vendor, or integrated into the valuation software. And also previously, I have been working with the commercialization manager at PNNL to reach out to different partners, talk about the opportunity for commercialization. And I think it's ongoing work. We will keep reaching out to potential collaborators and also software developer consulting company to talk about how we can transfer the technology we developed to them.
So it may be integrated, but there will still be a core functionality that is available that people can access through the lab. So
yes, I think the key value of here is not the graphical interface or those kind of design of the website, right? The value lies in the engine behind the tool, right? So those engine is the powerful weapon for the evaluation of energy storage.
All right. Well, I see we ran out of time. Thank you again, Dee, for your presentation. It was great to see how all that fits together from the modeling to a actual dispatch strategy. I want to thank all of our attendees today, and thank you for all your excellent questions. And sorry we couldn't get to all of them today, but I want to remind you, so this is an ongoing series that we're having in 2 weeks, April 28th at the same time. Wei Wang will be talking on flow batteries and giving you some insights into where flow batteries are today and where they are going. So with that, we look forward to seeing you in 2 weeks. Thank you for your time, and thank you for attending the Energy Storage at PNNL webinar. Take care. Thank you, everyone.